Yeah, this is 7 years after the publication of the Dyson papers that basically do all of this to say, hey, you guys have been saying the same thing the whole time. You know, why not both? These are correct. And then it also, I can get rid of the infinities for you guys too. And then like, so that was huge, right? Now you get this complete theory. And then Schwinger goes on 7 years later to be like, what have we done? We've created a monster. Okay, so this segment of the stream is going to be basically like I acquired a large amount of textbooks this week through unfortunate circumstances, not through good circumstances. Through unfortunate circumstances, I have acquired a very, very large amount of textbooks. Inside the textbooks, there is a lot of cool things. There's a lot of older books, okay? And I have been just reading some of the things, notes from my former advisor and like prefaces and forewords and things like that from people. And some of the stuff I found is really cool. So I have 3 things I wanted to read today. Just short little paragraphs and discuss the things from those books. So, yeah, so we'll read some of them, and then I think they're kind of interesting. We'll talk about history. It's more of a history thing, which I think is really cool. So if you have any questions about anything physics related, do the ask. You can do exclamation mark ask. Otherwise,
that was rude.
Yup. Let's do some reading. So, one of the books I got is the Feynman Lectures. A very old copy of it. This was printed in 1966. This is the 4th printing of the Feynman Lectures. The first one I think was printed in 63. So is that right? I guess in 3 years they printed it 3 times. Interesting. I assume that just means like the 4th edition. Now, you know, I've said it once and I've said it a million times that like Feynman, you know, my philosophy with him was you can learn from all of the good things he did as much as you can learn from all of the mistakes that he made, you know. So you can learn from the good and learn from the bad. He was an excellent educator. And it's always good to learn from those good things that he did. It's probably all in one now. I have 3 volumes of it for the old ones, and it also came with the exercises, which I thought was really dope. Like old exercise books. This is the thing we're doing after stream. It's called Old Man Reads from Old Books. Oh, it's 3 large volumes. But anyway, so this is the cool exercise booklet that came with it back in the day. So I thought that was pretty cool. But I wanted to read some of the things that Feynman said in 63 that I thought were interesting. So, and I thought that were nice. But basically his idea, so the preface kind of goes about like how he noticed that there's a spark missing in students after they get to intro physics, right? Because there's always these fun, exciting things. And I think this is even relevant now. There's always these really fun and exciting things. And then you can have a teacher, a physics teacher, who does intro physics and just drills it out of you. Like they just take all of the fun, they just take it, they just bundle it up, and just squish it and throw it in the garbage, right? And our job as educators, you know, whether or not you educate professionally or for funsies, it's important to always, like, you know, you want to make sure that people realize that the fun stuff is expiring. Like, that's cool. Like this, like all of the rigor, the stuff that we did, can get a bit boring, but it's super important if you want to be able to work on the cool, fun stuff, right? Like it's just super, super important. And that was what Feynman, that's one of the reasons why Feynman worked on the course, and that's what he says in the preface of this book, is that he wants to make sure that students still enjoy physics and that it's not just wrung out, like all of the fun's not just wrung out of them by, you know, introductory physics teachers who don't care about fun, who just want, you know, their grades to be a certain way. And I've seen it, and I'm sure you guys have all seen it. It's like a lot of physics teachers just want their grade book to look a certain way. They just want the students to feel a certain thing. And oftentimes it's not inspiration, it's struggle or... yeah, so this is going to be the end of the preface on the Feynman Lectures. That's what we're going to be reading. So again, remember, leading up to this, it was a... he was lamenting about how so many times students they lose interest in the course. So, all right, let's read what Feynman says. June of 1963. So again, up to now, he was lamenting about the fact that students often get left behind with the whole rigor. They don't like rigor. So still, I don't want to leave any student completely behind, as perhaps I did. I think one way we could help the students more would be by putting more hard work into developing a set of problems which would elucidate some of the ideas in the lectures. Problems give a good opportunity to fill out the material of the lectures and make more realistic, more complete, and more settled in the mind the ideas that have been exposed. I think, however, that there isn't any solution to this problem of education other than to realize that the best teaching can be done only when there is a direct individual relationship between a student and a good teacher. A situation in which the student discusses the ideas, thinks about the things, and talks about the things. It's impossible to learn very much by simply sitting in a lecture or even by simply doing problems that are assigned. But in our modern times, we have so many students to teach that we have to try to find some substitute for the ideal. Perhaps my lectures can make some contribution, perhaps in some small place where there are individual teachers and students, they may get some inspiration or some ideas from the lectures. Perhaps they will have fun thinking them through or going on to develop some ideas further. I think, this is by Feynman in June of 1963. I think what he says is very important and very valuable. I do have a couple problems. And he's always, like, so, I like Gelman. I like Murray Gelman. Sue me, I like Murray Gelman, okay? Jeez, sue me. And he always said something where it was like every single chance that Feynman can get, he'll make the story about himself. And then, like, I hated reading this at the end and just seeing this. It's just like, I hope my lectures reach and inspire everybody. It's like, I know there's nothing wrong with it and everything like that. It's fine for him to say that, but it's just like, I get it. I get it. I'm being picky. But anyways, the message of he complained that Feynman everything about himself. Yeah. He said that so Gelman was very much self-absorbed as well. But I would say that, his complaint was that Feynman would take every situation and turn it to an anecdote about himself, regardless of like how true it was or anything like that. But anyways, it's just my own. Every time I like see Feynman talk and then he starts talking about himself, it's just like But the overall message of this is really good. That the problem with education, you can't just sit in a lecture. You can't just absorb information that way. Having an individual relationship between a student and a good teacher, that's obviously the best, because then the teacher can bring out the best in the student, right? Like, nobody thinks that that's not true. And then, well, I mean, it depends. I guess there's situations where that's not true, depending on the teacher, namely. But yeah, and then he goes on to say, but in modern times, we have so many students to teach that we have to find a substitute. And I think that's true, and this is not a problem that was fixed by his lectures. Like, this is a problem that is true and would always be true. And that's the next community fundraiser where I have a robe and a pipe. But I think that's really cool. It does hit the nail on the head. A huge problem that we have right now is that everybody learns in a very individualistic style. And we don't have teaching for individuals right now. We have teaching for, like he said, 180 students in a packed auditorium. I knew lots of teachers who believed that was not true. I'm sure you did. They are what we call in the business wrong. Listen, I mean, the guy worked on Atomic Bomb and knew how to have fun. Listening to Los Alamos from below never gets old. I'll have to listen to that. I and a few others have talked about it. I'm convinced that Schwinger was the real outstanding intellect. Maybe he just shouldn't have written a. Maybe he just should have written a book like Feynman. I heard that he was like impenetrable to talk to. Like it was impossible to talk to him. I heard his notes were like, or his classes were brutal, as far as like the opposite of having an individual relationship with a teacher. He would like, I heard he would like come in, start at the top side of the board, finish, like he would come in wicked late, he would finish like at the very bottom end of the board, like the complete opposite diagonal side, and then just like immediately walk out, not answer questions, not talk to anybody. The next book, Quantum Electrodynamics by none other than Schwinger. Schwinger was, I would say it's Feynman's equal. He's not totally unrecognized. I would say Schwinger was Feynman's equal at the time. And we'll talk about the two of them in a second, but I wanted to read the end of this because it's kind of interesting. And then we'll talk about the two, and then we're going to talk about the two with another not-so-old book, still read by an old man. Those notes are available? Interesting. But this is basically, so Quantum Electrodynamics it's edited by Julian Schwinger. It's a bunch of papers that he put together. He goes on in the beginning of the preface to basically talk about how anybody who puts together a book like this is going to be biased. He goes on to say, I put this book together being biased. But it's really good. It's a really good thing, and it basically talks about the kind of like the progression of the development of quantum electrodynamics. Day 1, electrostatics. By day 2, quantum curve space-time. I think Schwinger was interested in things that would be relevant much later, like non-perturbative problems in quantum field theory. Yeah, I appreciate that too. I think this is leaving me with some questions. But the goal today is to talk about Schwinger and Feynman, and then subsequently Dyson. And we're going to connect the three together by reading things that they talked about in old books. Tominaga, I don't have a lot of stuff on Tominaga. Obviously, he has a bunch of stuff in this book because he was he had a huge hand in developing the Schwinger model, right? He was involved heavily in developing the Schwinger model. It was Schwinger and Tominaga on one side and Feynman on the other side. And we'll talk about that in just a second. But let me read what Schwinger wrote. So in this, like I said, he talks about. Let me turn the music off. It's a little too hype for reading a book from 1956. So, and then we'll turn it back on. So the preface, written by Schwinger in 1956 when he is a professor at Harvard. He wrote at the very end. So like up to this, he's like recounting all of the history of recounting all the history of the QED. It says, the post-war developments of quantum electrodynamics have been largely dominated by questions of formalism and technique, and do not contain any fundamental improvement in the physical foundations of the theory, which I think is a crazy thing for him to say, but cool, very interesting. Because to me, in my mind, this was always like, I thought everybody was just like, look at all the things we're doing. But yeah, it was a bit heavier than that, right? He's just saying, like, he doesn't think that any of the progressions are making fundamental improvements. Now, this is 1956, which is important because something happened a few years earlier than that, which was very monumental to all of QED. But such a situation is not new in the history of physics. It took the labors of more than a century to develop the methods that express fully the mechanical principles laid down by Newton. But we may ask, is there a fatal fault in the structure of field theory? Could it not be that the divergences, apparent symptoms of malignancy, are only spurious byproducts of an invalid expansion in powers of the coupling constant and that renormalization, which can change no physical implication of the theory, simply rectifies this mathematical error? This hope disappears on recognizing that the observational basis of quantum electrodynamics is self-contradictory. The fundamental dynamical variables of the electron-positron field, for example, have meaning only as symbols of the localized creation and annihilation of charged particles, to which are ascribed a definite mass without reference to the electromagnetic field. Accordingly, it should be possible, in principle, to confirm these properties by measurements, which, if they are to be uninfluenced by the coupling of the particles to the electromagnetic field, must be performed instantaneously. But there appears to be nothing in the formalism to set a standard for arbitrarily short times, and indeed the assumption that over sufficiently small intervals of the two fields behave as though free from interaction is contradicted by evaluating the supposedly small effect of the coupling. Thus, although the starting point of the theory is the independent assignment of properties to the two fields, they can never be disengaged to give those properties immediate observational significance. It seems that we have reached the limits of quantum theory of measurement, which asserts the possibility of instantaneous observations without reference to specific agencies. The localization of charge with indefinite precision requires, for its realization, a coupling with the electromagnetic field that can attain arbitrarily large magnitudes. The resulting appearance of divergences and contradictions serves to deny the basic measurement hypothesis. We conclude that a convergent theory cannot be formulated consistently within the framework of present space-time concepts. To limit the magnitude of interactions while retaining the customary coordinate description is contradictory, since no mechanism is provided for precisely localized measurements. And then lastly, he just says, in attempting to account for the properties of electron and positron, it has been natural to use simplified form of quantum electrodynamics in which only these charged particles are considered. Despite the apparent validity of the basic assumption that the electron-positron field experiences no appreciable interaction with fields other than electromagnetic, this physically incomplete theory suffers from a fundamental limitation. It can never explain the observed value of the dimensionless coupling constant measuring the electron charge. And then he goes on to talk about a little bit more about renormalization. And let's skip to the end. Yet the real significance of the work of the past decade lies in the recognition of the ultimate problems facing electrodynamics, the problems of conceptual consistency, of physical completeness. No final solution can be anticipated until physical science has met the heroic challenge to comprehend the structure of submicroscopic world that nuclear exploration has revealed. Boom! Julian Schwinger, Cambridge, Massachusetts, at Harvard, 1956. All of these problems that he talks about are still there. Like, he's concerned in 56, which I think was like super crazy. Okay, hold on, let me get the music back. He's concerned in 1956 that there won't be a solution to the measurement problem. That the whole idea that we've built the quantum field theory the way we did will always result in, I don't know about always, but he says at the end, like we need to have some sort of thing happen to change that. You know, like this is, it's the way that we're doing it right now, finding a measurement, saying that we're going to find measurements of like what that means is going to be self-contradictory. There's a major, big example of this happening in the recent future, where one of these things that we use in quantum field theory was supposedly solved for like the 100th time. It turns out it was not solved, which was the derivation of the coupling constant, or I'm sorry, fine structure constant, which we can rewrite as the coupling constant of the, you can treat the fine structure constant as the coupling constant in QED. That was recently proven to be solved, or not proven, it was recently attempted to be solved by Michael Atiyah. And I don't know if you guys remember, this was a few years ago. It was like a huge deal where like he said he solved it, and then it turns out that it was like, you know, after everybody reviewed it, it was just like, it's not really a solution. And there's been other people who said it as well. But yeah, it's crazy that like, that Schwinger was concerned at the onset. This is 1956, okay? At the onset of QED, and I'll tell you why this is why I say the beginning of QED, that this was he was worried that this was the end of physically understanding QED. I don't know, it depends on if you want to physically understand something or not, right? He's saying the same things that I always say, right? That the measurement has no, the measurement is not, we don't know anything physically about a particle before we measure it. And he wants to know what that mechanism is for making everything happen the way it happens. And we wrote quantum field theory in a way, and that's what he's saying. He's saying we're writing. He's one of the fathers of quantum electrodynamics. And he's saying we made this in a way where the physical properties behind the coupling constant and the measurement are going to be hidden behind it. And you won't know them. And I think that was wild. I thought that was one of the coolest things ever. Now, I say that this is the beginning because in this not as old book, Steven Weinberg, The Quantum Theory of Fields, he talks about this. Now, you guys may have heard of Feynman Dyson, passed away this year. Or was it this year or last year? Very recently. Hugely contributed to physics, but a lot of people might not know why. Okay? So this is from Steven Weinberg's volume 1 of his quantum field theory, okay? And this ties everything together, all of the names that I said tied together in this paragraph. Finally, in a pair of papers, this is page 37. Finally, in a pair of papers in 1949, Feynman Dyson, 1949, Feynman Dyson showed that the operator formalisms of Schwinger and Tominaga, did I say that right, Tominaga? Would yield the same graphical rules that had been found by Feynman. So Feynman developed path integration into Feynman diagrams. Schwinger and Tominaga did what's called the canonical formalism, where you have Wick's theorem. Basically, you just draw every possible diagram, and then in every possible direction of time, and then cancel a bunch of symmetry factors out, and then do it all up. And so he did that with Wick's theorem and normal ordering and time ordering and all that jazz. And then, well, they both have time ordering, and then Feynman did path integral, right? So then Dyson also carried out an analysis of the infinities in general Feynman diagrams and outlined a proof that these are always precisely the sort which could be removed by renormalization. So he showed that you could renormalize the theory, which is important because all of these, the mathematical errors that Schwinger was talking about were all these infinities that were showing up by just adding, you can add up infinite diagrams and make terrible probabilities. Who wants a probability of infinity? That just means your math is wrong. So Dyson did that, and then also one of the most striking results that could be inferred from Dyson's analysis was a criterion for deciding which quantum field theories are renormalizable, in the sense that all infinities can be absorbed into a redefinition of a finite number of coupling constants and masses, in particular, an interaction like a Pauli term, which would have changed the predicted magnetic moment of...
I hate you.
Shh. Which, don't interrupt my reading. Which would have changed the predicted magnetic moment of an electron, would spoil the renormalizability of quantum electrodynamics. With the publication of Dyson's papers, there was at last a general and systematic formalism that physicists could easily learn to use, and that would provide a common language for subsequent applications of quantum field theory to the problems of physics. Again, boom! So now, we have the work.
I go to the bathroom now.
I beat you. See, there's the old man typing away at the keyboard. I'm going to speak and interrupt him. Except it takes you 10 minutes. I was reading quickly. I was like, he's going to try to speak. I got to get this out. Oh, man. That's funny. Sorry, Tyrion. What's it? How did you do that? Anyways, so here we go. We got 1949. So before 1949, we have these crazy two ideas, right? That you have, in one of them you can...
your nose.
You could have one of these set of, canonical formalisms of getting all these different amplitudes that go into the S matrix to, talk about probabilities of scattering, blah, blah, blah. And then on the other side, you have Feynman diagrams. Amplitudes exist as the different paths that make up the path integrals of configuration space, right? And these, and then the path, and then you can derive the Feynman rules and Feynman diagrams. So now, all you have is this really nice little set of Feynman diagrams, and you can draw all the diagrams and evaluate all of the things. Yeah, so then you can derive all these different things and all these different diagrams, and each of them you can write an integral associated with that diagram and then evaluate that integral, and you get a probability amplitude and all that good stuff. But the problem is that you have infinitely many of these diagrams, and all of these diagrams add up to infinity. And that doesn't make sense. You can't have infinitely probabilistic outcomes, right? Yeah, so then Dyson comes along and says, why not both, right? You can take the work by Schwinger and Tominaga. You can recast it into Feynman diagrams in a very easy and usable way. You get the diagrams back, and then these infinities, you can actually basically subtract infinities away, natural infinities that come out. And if you guys want to know where that is, there's, if you want to know what I'm talking about with that mathematically, I have the path integration series on my YouTube channel has those videos about this, right? So then Dyson comes along and he's like, okay, so we can subtract those infinities away by using fine logic, right? They do that, and like I said, I go over that. I use Shred-Nicky, so you can follow that too. And then what you get is a completed quantum electrodynamics system that follows both of the formalisms, and in the end, you just get these nice Feynman diagrams that, again, just translate into integrals that you can solve, and you get definite amplitudes of scattering, very, very accurate. This is the theory. The quantum electrodynamics is the theory that was accurate for an magnetic moment of an electron by like 12 or 13 decimal places. So it's a great theory. It has to be correct. It's just way too accurate with experiments. Over and over again, it proves to be true in experiments, right? So then Schwinger is like, so this is before they did all that stuff, right? So this is 7 years after the publication of those. Yeah, this is 7 years after the publication of the Dyson papers that basically do all of this to say, hey, you guys have been saying the same thing the whole time. Why not both? These are correct. And then I can get rid of the infinities for you guys too. And then so that was huge, right? Now you get this complete theory. And then Schwinger goes on 7 years later to be like, what have we done? We've created a monster. If you want to know about the physical explanations that are behind the measurement problem, we have just screwed that up. And we proceeded to develop quantum field theory despite his warning. And now I wonder if there's ever any going back. Is there anybody who can go back to Schwinger's warning and be like, I got to rederive quantum field theory? I assign that job to Justin. Good luck, Justin. We're all rooting for you.